Good evening, ladies and gentlemen. My name is Jeff Badnock, and on behalf of the University of Montana Alumni Association and the Community Lecture Series Committee, it is my pleasure and honor to welcome you to the 22nd Community Lecture Series here at the University of Montana. First off, silence your phones. Don't be that person. Thank you. This past week, the lecture series lost a friend, faculty member Dr. Dustin Hollis, who was one of our presenters last year, passed away after a very short illness. And he was a large man with a large personality who was well loved on the university campus, and there will be a memorial service, or not a service, but a memorial celebration of his life this Friday the 15th at 4 o'clock in the UC Ballroom if you would care to come and participate in that. This year's series, Shoot the Moon, is a series that was put together in recognition of several anniversaries that are going to be talked about in the course of the lecture. Our format is each week for the next tonight and the next 5 weeks after this is a University of Montana faculty member will present a lecture, and after the lecture, the audience is invited to ask questions and make comments. This is like going to college without the tests or the exams or the projects. So there's that. MCAT, as always, is recording these. So during the question and answer period, we will have microphones that we'll be able to hand around the auditorium. If you're going to ask a question, please do like I'm doing. Speak directly into it. Don't hold it down here. Talk right into it. So we make sure that we capture your question. For the people who see this on video, if all they hear is and then the answer, it's not a very good experience for them. So please help out the other people in the auditorium and our future viewers by letting them hear your question. I have a friend who is a poet, and she insists that whenever you embark on something like this, that we invoke the muse with a poem. We did this for the Bird series, and it seemed to work very well for us. So tonight, I'd like to read for you a poem by E.E. Cummings called "The Moon Looked Into My Window." The moon looked into my window. It touched me with its small hands, and with curling infantile fingers, it understood my eyes, cheeks, mouth. Its hands, slipping, felt of my necktie, wandered against my shirt and into my body. The sharp things fingered tinily my heart, life. The little hands withdrew jerkily. Themselves quietly they began playing with a button. The moon smiled. She let go my vest and crept through the window. She did not fall. She went creeping along the air, over houses, roofs, and out of the east toward her a fragile light bent gatheringly. E.E. Cummings. Our speaker tonight is Anna Klene, and she will be talking tonight. I also wanted to point out that in the program, all the biographies of the speakers are in there, so I'm not going to take up our time with that. But Anna's topic tonight is, help me, 60 years of NASA and the atmosphere. So, Anna Klene.
Thank you. Thank you. Can you hear me okay? Okay. Louder. I'm always being told that I need to project. So we're celebrating a whole lot of anniversaries here in this last year and this upcoming year. And just before we started talking about this series, I saw this cartoon that basically it's been 57 years since the first human airplane flight to the first human space flight. And it's now been that long, and this was last year, since that. So spaceships are now older than airplanes were when we flew our first spaceships. It seems like we should have robots in our houses by now, or some other spectacular thing when you think of it this way. Last December, it was the 50th anniversary of the Apollo 8 mission, where man stepped on the moon for the first time. And this picture was one of the images that was taken. And I think a lot of people have a very strong emotional reaction to this image. We keep taking them. This was taken just last week by the Chinese satellite, which I won't try to pronounce the name of. And they just landed a lander on the dark side of the moon. And so they have another satellite that's going around, and they wanted to get a picture. Evidently, if you zoom in really far, you can see their lander on the dark side of the moon there, and then the Earth below. There's a space race going on that we don't talk about very often in the U.S., and that's the fact that India and China are fighting to be the third nation to do a whole lot of things, including land on the moon and all sorts of things that we're thinking of as 50 years ago. They're trying to do today to improve their space capabilities. The module pilot for Apollo 8, William Anders, said that when he got to the moon, what he learned was that we came all this way to explore the moon, and the most important thing is that we discovered Earth. And I'm not going to talk to you a lot about the moon today. I'm afraid this is pretty much it. But one of the big missions of NASA is to explore Earth. And partly that was part of their mission was that we had to figure out how to navigate through the atmosphere and get through all of that mass so that we could get into space and then figure out how to get back in too. But also we just realized that there was so much that we could learn once we started getting into the atmosphere. And so I'm going to talk about a history of atmospheric research, starting actually a bit earlier than the founding of NASA. And also because of the two next speakers, Steve Running will talk to you about satellites. I'm going to try to not talk about what we've learned about the weather with satellites. And I'm not going to talk too much about the history of the space race, because Mike Mayer is going to do that. And so it's a bit of a challenge for me to talk about the history of the atmosphere without doing these two things. And I will totally talk about a satellite at the very end, because I can't resist. I should also mention that I teach weather and climate classes, but the other thing that I teach a lot of is remote sensing, so the analysis of satellite imagery. So some of my very good stories are not going to be here tonight. But Steve has funnier ones. So. One of the other questions that might come up is, why are we talking about NASA and weather when that's something that NOAA does? And NOAA is the National Oceanic and Atmospheric Administration. And their job is to provide us with weather forecasts. Their job is to keep our airplanes safe, our trains safe, our ocean liners safe. Day to day, they are our weather source. NASA, on the other hand, is a research body. They were designed and developed and set up to do research, to help us get to space, to learn about our atmosphere. And so they really work together. When we have things well established by NASA's research, we turn them over to NOAA, and NOAA implements them faithfully day after day with standard routine protocols. NASA, though, is tasked with the research. And so when there's questions that we don't know the answers to, or we don't know how to measure things especially, we go to NASA. And so quite often with complex problems, we have funding coming from NASA and NOAA to help us figure out when we find that there's something new with the weather we didn't know. We're probably relying on both NASA and NOAA to help us figure out that next step. So here goes the history. We've been taking notations about weather and very faithful, careful weather observations for quite some time. Our founding fathers were very obsessed with this. And the bottom is just getting cut off, so there are a few notes here I can see that you can't. Is that a little better? I'm going to try to be careful. A handheld? think he can change it up there.
Can you turn it up, John?
Is that better? Okay. I have a mic. How about that? Is that better? No. Okay. I will try to talk louder as well. Okay. So the founding fathers were very fond of weather observations. And if you think back to before you could turn on the radio and get the daily weather forecast, we really had an interest in having our own source of information. The chart on the right is a page out of Thomas Jefferson's weather observations that he took for over 50 years on a daily basis. Benjamin Franklin is often credited with an experiment with a kite. But one of the other things he did was try to get other people to tell him their weather observations. And he would map them and chart them. And so he was one of those people who first described the fact that weather patterns in the U.S. tended to move from west to east. When we invented the telegraph, we started getting people transmitting those observations much more quickly than they had to send them by mail to Franklin. And so there were several different people who started working on getting telegraph networks together to send in weather observations. So Joseph Henry was the first secretary of the Smithsonian, and he set up a group of people who would send in their weather observations, and he would draw them on a map by hand each day in the Smithsonian. In 1843, we had the first official meteorologist for the U.S. government, and that was his title, James Espy. And he constructed this map on the right showing where winds were coming from. And generally, the arrow is pointing the direction the wind is coming from towards that city that's the observation. And this is a map from 1849 showing that telegraphic network of people who were reporting in these observations. So we could start to chart the patterns of these different weather variables that we were measuring. By the 1870s, the Army had decided that this information would be very useful and that they wanted to make sure that we were getting these observations regularly. And so they turned over the weather reporting task to the U.S. Army Signal Corps. And about 20 years later, that was turned over to the Department of Agriculture, and that was the formation of the U.S. Weather Bureau, which will become the National Weather Service, because there was an agricultural application as well. And so all of these people were wanting these weather observations. And there's a whole series of buildings that look very similar to this one here that were built all over the U.S. where these weather stations were implemented. The one in Barrow, Alaska looks very similar to the one in Maine. Some of them are brick and look a little tidier, but the smaller ones look very similar. And so once we had these systematic observations being taken, we could start just making a map of whichever variable we wanted, whether it was pressure or temperature or wind speed. And so we could start developing these maps of the world if we could get them all communicating. Europe was definitely doing very similar designs of weather networks at the same period. And so we could pick a variable like pressure, and we could map it globally. Or air temperature. This is one that we're pretty used to seeing, and I think a lot of people are used to turning on the weather and seeing something that looks like this. The eastern part of the country being much warmer than we are, for instance. And if you squint and look at these maps, it wouldn't be hard for you to draw a circle around the red area. We very scientifically drew a red line around that red area and said that looked like a blob. And then we decided we needed a better name, and we decided that we would call them air masses. this is really how we define air masses. We pick a variable, and we look, and we see, is there a place where there's a distinct boundary around that? And to be a little bit more formal, we should say that the characteristics of that air mass are similar, not just in terms of one variable, but usually 3, 4, or 5. And we can map where on the globe these air masses form. They're typically going to form either over an ocean, like out here over the Pacific, or over a continent, say over the center of Canada. And if you think back to last week's weather with that Arctic air mass that we had in place, it formed over the Arctic in central Canada and then moved east and then came down through the Flathead and through the Hellgate into us. So in the 1800s, this is where we were. We could define an air mass. We could draw these maps. But in terms of figuring out how the weather was forming and interacting and changing, we weren't really too far. During World War I, we had advancing armies that would collide along fronts. And if you have two air masses that are moving towards each other, they can collide, and we decided that where they collide, we would call that a front. And the Norwegians, there's what we call the Norwegian School of Meteorology, and Jacob Berknes was the main leader of that school, developed what we call the polar front theory. It's sometimes called the Norwegian polar front theory. And basically, these two air masses march into each other, collide, and one of them wins. And it pushes the other one out of the way. And when we do that, we get a kink along the boundary where those two air masses met, and we form this little hook. And this is the invading air mass that is going to push the other air mass out of the way through time. The other big thing that was really interesting back in this day was that we also had the very first inklings of numerical forecasting. Berknes had gathered a whole series of weather measurements along the coast in England and Norway. And 6 years later, one of these army meteorologists took it and said, okay, if I had all of these observations at the same time, the telegraph networks not being super reliable during the war, if I had had all of these, could I numerically calculate what the air pressure, temperature, wind speed would have been at all of these places, enough to mathematically generate a forecast? It took him 6 weeks of calculations to do a 12-hour forecast. But at least he came up with the idea, and he divided the world into a grid. And this is exactly the way our fancy supercomputers run our models now. And it started here with this idea. I will say another thing that sort of supports the notion that these are fronts is that if you look on either side of a frontal boundary and you look at the wind, and these are streamlines to show the wind movement. In the early days of wind mapping, we used to play with this idea. But then when we went to those numeric models, it was really hard to show. And so for a long, long time, we had the little arrows pointing towards that station that we had on that earlier map. I was at the gym the other week, and I saw that some of the cable television stations are now starting to have these streamlines on their forecasts because they can animate them and move. This is the way we wanted to illustrate wind hundreds of years ago. We couldn't animate things on the page, and now we can. So if you just think about the wind motion, basically the streamlines get thicker as you get higher wind speeds. They also indicate direction, and on either side of the frontal boundary, which is this line here, we have wind on opposite directions. And so you can think about this as being a moving thing. This is a front. This is a battle between these two air masses on either side. And in some parts of the world, this model of weather works fairly well. In the eastern part of the U.S., it does a fairly decent job. But you'll see that this is not really the way we think of the weather anymore. We think of it as a much more dynamic system. The other thing is that all of these observations have been things that we're measuring at the surface. And if you think about the atmosphere as a complex fluid, there's probably things happening up above. And in the 1800s, people were pretty interested in this. They started out trying kites. And I recently tried to take some air photos with a kite. And I will tell you that taking scientific readings with a kite is very difficult. Balloons are much better. And meteorologists had figured this out. By the late 1800s, people were routinely putting weather instruments up on balloons. One of the big problems, though, was that you had to get the instruments back. And so you either couldn't let the balloon up too high, or you just had to chase it. And so there was a pretty big revolution in weather balloons in 1892, when a German Esman introduced rubberized balloons. And they would get so high in the atmosphere that, and at a certain pressure they would burst. And a little parachute would drop out, and your delicate instruments would drop to the ground. Usually you only had to go 10 or 15 miles to get them, as opposed to a couple of hundred as they had been before, or just lose them altogether. We have been taking balloon sonde data, sonde is the measurement, since 1904 routinely as part of our regular observations with the Weather Service. In the 1930s, we added a little radio transmitter. And so even if we don't get the instrument back, we get the data. If you're walking in the woods and you happen to see a little styrofoam box about this big, check to see if there's a label on it. Usually there's something along the lines of harmless weather instrument is the label. I meant to bring one over. But we launch these still today, twice a day, from a series of weather stations. They look remarkably similar to the balloons that we were using 115 years ago. This is the official U.S. network. We do not have one here in Missoula. Our closest radiosonde site is over in Great Falls. And so these, basically what these do is they take those measurements of air temperature, pressure, wind, humidity, up periodically through the atmosphere. Originally, they only took a couple before they stopped. And now we routinely get these going up to 100, 130,000 feet and travel several hundred miles. And we get that profile up through the atmosphere. So we're not just on the ground, but we're now getting this vertical view of what the weather's doing. Scientists being scientists, we wanted more than just a few observations. And so the scientists wanted to go up in the balloons themselves. And in 1862, the British Association for the Advancement of Science hired a well-known balloonist, Henry Coxwell, and a local scientist, James Glaisher, to go up and try to take measurements as high as they could. This sounds perfectly reasonable, except that we didn't know that much about the atmosphere. And so as they're going up, Glaisher is writing down measurements as fast as he can take them. He's trying to measure the barometer so that he can figure out his altitude. He's taking the temperature and the wind. And they did observe that the wind speed changed dramatically as they went up, getting faster and slower. They also noticed that it was getting colder, to the point where Henry Coxwell's hands were turning black. He was doing better than Dr. Glaisher, who was feeling a little dizzy and then a little nauseous, and then just slumped over. It was about that time that Coxwell realized that his hands were no longer working. And the way that they were going to get down was for him to release the valve to start letting pressure or air out of the balloon. I think it was actually a helium mixture. And to do that, he had to reach up here. But his hands weren't working. And so he couldn't pull the string. and his companion was incapacitated. And so finally, the story goes, he managed to scramble up using his elbows and then jerk the pole with his teeth. The third time, it actually released a little air and went down. And then he managed to get it and I think he probably just leaned back. They managed to drop 19,000 feet in 15 minutes and safely land. Both of them went ballooning again, which I don't think was a wise decision. They later calculated that they got up to about 35,000 feet, which is where some of our jet planes fly today. This is the nicest story. Most of the other people did not survive the mishaps that they had with balloons. I didn't put any of them in. I will also say that we did do things like take pigeons up and try to see how they would respond at different altitudes, and that didn't go well either. But ballooning was a very high mortality sport. It was, I saw a quote that it was much more dangerous than serving in the military. And serving in the military in World War I was not a safe pursuit. We continued trying to measure higher and higher in unmanned balloons as well. And Richard Asman, who had invented the the balloon sonde, within several days of the Frenchmen to rest the board, both managed to design balloons that could go up high enough that they measured a place in the atmosphere where the temperature didn't drop anymore. And all of our experience had been that it just got colder and colder and colder as you went up. But then within 2 days, in 1902, these people both published the fact that between 10 and 15 kilometers in the atmosphere, the temperature stayed the same, and then it actually started to warm up. And we now call this the tropopause. It's the top of our layer of atmosphere. This is the part that we live in. And if I show you a diagram from one of these textbooks, we live down here at the very, very bottom. And this is the only part of the atmosphere that we were really familiar with. Here's Mount Everest over here for scale. I like this diagram because it shows you what's happening in the different parts of the atmosphere. And so a lot of people climb Mount Everest with supplemental oxygen. And so these folks were trying to go up, several thousand feet, or 35,000 feet into the atmosphere, and they're getting there and they're not having supplemental oxygen because they didn't really know they needed it, for one thing, at the beginning. But we still want to know what's higher, right? And also point out, this is the tropopause. This is where that temperature, this is a graph that shows temperature as this yellow line here. And so you can see that it gets colder with height as we go up. And we're pretty confident about that most of the time. But then it pauses, and then it warms again. And then it pauses and cools again, and then pauses and warms again. And we use that to define the different layers. And so the breaks there are each a pause, referring to the layer below them. So we haven't gotten that high in our atmosphere yet. And people are still curious about what's going on. Actually, I should go back. Oops. I'll also point out, we generally define the top of the atmosphere as somewhere between 50 and 100 miles up. And I'll come back and talk about that a little bit more. Up here is where we have the auroras. Here's the stratosphere. Here's the stratosphere or ozonosphere. And this is the mesosphere. And we'll come back and talk a little bit about some of these things, but mainly about the ozonosphere and this gentleman. So in our quest to go higher and higher, it had become apparent that if we wanted to be in the balloon making the measurements, we needed to do something so that we didn't pass out or freeze our hands. And so in 1931, a physicist, Auguste Piccard, and his assistant Paul Kepler, built this pressurized aluminum capsule. And they went up to a height of about 45,000 feet, or almost 10 miles, which was the record at the time. Auguste Piccard was an interesting fellow. He was a physicist. He was trying to make observations on the theory of general relativity and also cosmic rays. So he was definitely doing science as he was going. He must be quite a colorful character. They've written an opera about him called Piccard in Space. And if you're familiar with Star Trek, this is where the name Piccard came from. Supposedly he was 6'6". So that was 1931. Generally around the 10-mile boundary, we will say that that is a person going into space. And in 1934, August's brother Jean and his wife Jeanette, who was an American, also went up in a balloon. The first time they went up to about 16,000 meters. And the next time they went up a month later, she was the pilot. She was the first lady to get her pilot's license in the U.S. and the first one to pilot a balloon up to over 10 miles and basically reach the stratosphere. After her husband passed away, she started working as a consultant for NASA in the 60s. So this is our first time I can slip NASA in here. So there should be some things going on in this upper part of the atmosphere, and yet we really haven't found very much. We knew that the wind speeds were changing. We were measuring some of the chemical composition. We were learning some of the things about the cold. People were making measurements, but we still really weren't understanding the dynamics of what were happening. And in 1944, we had just introduced the B-29, which was able to fly higher than many of the previous planes. And so what this meant was we were getting higher up in the atmosphere. And so we were flying at something like 22,000 feet, 25,000 feet. And the calculations showed that as we went higher in the atmosphere in general, the wind speed should be faster, up to 150 miles an hour, which was higher than we had been flying before when we were flying lower. And so we're under all this pressure, and so they started sending the bombers out. And they calculated fuels based on what they thought the flying times would be at 150 miles an hour. And they figured the targeting for the bombs based on how things would fall if there was this nice even flow and an increase of speed with height. But things didn't go quite as planned. In some cases, they would get there much sooner than they thought. And in other cases, they would get there much slower than they thought and not have enough fuel to get back. And it didn't take but a few weeks for people to start figuring out that something was really dynamic up there. They also noticed that as they dropped the bombs, they would start to scatter in really haphazard ways, and they would sometimes see them kind of all slow down after they had dropped them in a very dramatic fashion. And what they had done was they had discovered the jet stream. We just didn't know it was up there because we hadn't had a lot of people sending multiple balloons up to see that 50 miles south it was a whole lot slower than it was 50 miles north. So now we know of this jet stream as this really thin ribbon of air. Sometimes we call it a river, and if you're familiar with river dynamics, if you boat and you think about the meanders and swirls, it's very much the way the jet stream works. If you picture a cold air mass up over Canada, which is where it usually is, right? And think about warmer air masses coming from down to the south, where they meet, up at the very upper levels of where they meet, at the top of the front, there's a tremendous difference in the density and the pressure on either side. And this little narrow ribbon or flow or river of air gets to reach really fast speeds. These speeds can be 200 miles an hour or more, and just routinely, and they can get stronger. It also varies dramatically from one 4 or 6 hour period to the next 4 or 6 hour period. It will increase and it will slow down, very much like a river. It just flows and moves and changes all the time. In terms of just how big it is, it's only maybe 3,000 to 7,000 feet deep, maybe 100 miles wide, maybe 300 miles wide. Depends on the day and where it is. They're faster in the winter than they are in the summer. So it's this very dynamic ribbon that we were trying to predict where it was. And if you think about it, you live here and sometimes the jet stream is over us and sometimes it's not. It really varies widely in terms of where it is. And so predicting that was a bit of a challenge. There was also a really ironic point to us discovering the jet stream this way. And that was a Japanese researcher had discovered it first. In 1926, he had been making a series of measurements using balloons from mountaintops observations in Japan. And he would send off the balloons either on the mountain or on the west coast. And he would track how far they got to the east coast. And he would notice that sometimes they got there much faster than others. And he had published his results, just like a good scientist does. But he was also the head of the Esperanto Society. And so all of his results were published not just in Japanese, but in Esperanto, which had even fewer speakers. And so nobody really knew about his observations, except the Japanese. And so when the bombing intensifies, they also knew about the jet stream. And so they countered by deciding to send 9,000 balloons laden with explosives and use the jet stream to bomb mainland U.S. And they did, over about 8 months, send 9,000 of these balloons laden with bombs and ballast. And there was a series of instruments here such that when it reached certain heights, it would drop ballast to keep it in the jet stream as much as it could. About 10% are thought to have actually made it across the ocean to the U.S. We've documented about 900 locations where we think they landed. They only caused 6 deaths that we know of. One landed in Oregon, and a family on a picnic saw it, went over and tried to play with it and figure out what it was. And only 2 of the family members survived. There was a press embargo as soon as these started hitting, and it is credited with stopping the Japanese from sending more, because they were managing to get about 10% to land. I don't think the explosions were as efficient as they had designed them to be. They also thought that when they crashed, they would probably start fires, and there's only a couple that were documented. But really, the analysts tend to say that it was the embargo, the fact that even when we started getting them reported hitting places, that there was no press coverage. Those reports were sent to the War Office and nowhere else. But the Japanese gave up after 8 months because they didn't think any of them were making it. The winter jet stream is typically pretty much going from Japan over to the coast, and this is a map. If you think the jet stream isn't very active, this was over 8 months. They all landed, or they all were sent from here. The Army had geologists test the sand, and they were pretty sure that it was coming from this part of Japan, in the ballast. I'm also saying jet stream like there's one, and in the U.S. we tend to be pretty, we exert a lot of ownership over our jets. There's 4 jets usually, and sometimes 5. There's the polar jet stream, which is the one we're used to up here in the northern hemisphere. There's one in the south as well. There's also a subtropical jet that tends to form between the really tropical air masses and the continental air masses that form in the mid-latitudes. And then periodically in the summer, we get an equatorial jet that forms right usually here, just near the Himalayas, that flows counter to the others. And so if you think about this, we have a very dynamic atmosphere with 4 jets wiggling around most of the time. And you guys are all pretty familiar with this. This is the polar vortex. A vortex is just a low pressure system. And we've measured pressure all over the world. We have one over the Arctic and Antarctic pretty much all of the time. It's a low pressure, it's cold, the air sinks there. So the polar vortex doesn't suddenly form and attack us. It's just always there. It's just that sometimes it tends to flow in a nice concentric circle and behave itself. Oops, can I get that to play again? At other times, it wiggles and it has these loops called Rossby waves that basically are these dips in the jet. And this is just an illustration of wind speed. And you can see that up in the upper atmosphere, we have this river that forms, and you can see just how fluid it is. Sometimes it meanders, sometimes you'll have a cutoff loop, but it is very dynamic, and it's changing all the time. And you can see why we might not have known it was up there. But this is our polar vortex. Typically, if we have a stable polar vortex, on the left, we just have one strong jet stream that basically goes in a circle. The Antarctic jet is particularly strong this way. We have a continent of Antarctica surrounded by an ocean, and so that jet just almost always stays in a very, very narrow path. Ours meanders quite a bit more because we have a warm ocean that may be covered with sea ice or maybe not, and then these land masses alternating with oceans. And so we have good sources for wiggles to form and start in those Rossby waves. So I'm not supposed to talk about the space race, but I have to mention that NASA was formed. In 1957, Sputnik launched, and pretty rapidly thereafter, like by the following year, we had organized NASA. And basically what we did was we pulled together the existing agencies from a whole slew of groups. We had the National Advisory Committee for Aeronautics that had 3 research labs, Langley, Ames, and Lewis. There were a couple of smaller test facilities. They already had 8,000 people working for them. And then we just added in parts from other groups, like the Naval Research Lab in Maryland, or the Jet Propulsion Laboratory, which was for Caltech for the Army. We pulled in the Ballistic Missile Agency from Huntsville. And so we were pulling all these people together to try to form a civilian agency that was not military to work on aeronautics and space. And so it was a little bit hard for them to get some of these folks to give up that military route. But we had a military version as well that I think Mike Meyer might mention going on as well to try to militarize space. But NASA was supposed to be this civilian agency. That said, we had all these experiments going on because we had the military having this group of people who were working on aeronautics. There was 8,000 of them. And one of the experiments that they did in 1960 was send a captain up in a balloon, this time to 100,000 feet. So he wore a pressurized suit, because we learned that lesson. And why were we doing this? Well, we were getting ready for the space race. So we wanted to hear or see what people would do when we get them to really extreme altitudes, even if we have them in a suit. And we also want to know what would happen if something went wrong in the upper part of the atmosphere and they had to bail out. And so Joe Kittinger was the guy. And so they had him do a series of jumps. On the second one, he didn't jump correctly with the correct technique. And he started spinning at 120 rotations per second, they calculated later. And he blacked out, but his backup parachute went off. And so he went back up for the third attempt, and he made it to 102,000 feet for Project Excelsior, which is almost 20 miles. And this is a photo of him jumping out of the plane, or pardon me, of this basket. And this is at the National Air and Space Museum, and you can see him there. He went on to have a tremendous career. He was a test pilot for a while, and then he flew in Vietnam. He earned a bunch of distinguished service medals. And then in 2012, some amateur enthusiasts decided that they wanted to break the record. And he helped them prepare, and then 2 years later, so that was in 2012, and then 2 years later, another group went out and jumped from slightly higher. But on our diagram here, up until 2012, the textbooks always put Kittinger's balloon on there, because that's as high as we've gotten man to go up, not being in an aircraft of some kind. Pretty much, if you get to the tropopause right around 10 miles, you need to have a pressurized suit. Even below this, it's pretty typical for people to start losing consciousness because the oxygen is just so thin. As we keep going up, we do start wondering, well, where is that line? And as you go up, the concentration of the atmosphere just decreases. Through the homosphere here, this blue line, the gases stay mixed. And so you have the same percentage of oxygen. It's just that as you go up and up, you get less and less and less. And it's quite a curve. So that by the time you're here, you've got about 99% of the atmosphere below you. So you're getting to pretty low levels of oxygen fairly quickly up at this point. If you get above here, the gases actually start separating themselves by density. And so the heavier gases are lower, and the lighter ones are up higher. And right around here, too, somewhere near the top of the mesosphere, near the mesopause, is where you have so little atmosphere that you can't get lift anymore. And if you wonder what the difference is between aeronautics and space, or aerodynamics and aeronautics, basically, when you can't get glide anymore, we got to go to an aircraft that has its own power, that will be able to launch us out of the atmosphere. This is typically referred to as the Kármán line, but depending who you're talking to, even Kármán, he'll give you a little bit of a variation of where that line is. But it's somewhere right around the mesopause. So I think you're thinking that the atmosphere is a little bit more complex than we had thought back after World War I. And so once we got the jet stream and started being able to figure out where it was, we were still sending up our radiosondes, so now we could map where the jet stream was pretty systematically as well. We started realizing that there's a coupling between the lower part of the atmosphere and the upper part of the atmosphere. And so we revised our Norwegian polar front model, and we decided to come up with what we call the conveyor belt model. And in this one, we have air masses moving around on the ground, but we also have air from higher up, either as part of the jet stream or coming in around the sides of it. And we know that we get this complex interaction between air going up, air coming down. And the joy of the conveyor belt model is that we can't just apply this anywhere in the world. We have to customize it for every situation, because we know that we'll have more frequency of dry air if it's coming over a continent versus wet air if it's coming over an ocean. And so this conveyor belt works really well in the US and in parts of Europe, but we have to modify it for every other location. It does make you kind of want to go back to the simple map. Two fronts, they advance and they interact. But our forecasts are much, much better if we switch over to the conveyor belt model. One of the other things that we were starting to work on, right as NASA was getting started, was our understanding of oscillations. And you probably have all heard of the El Nino. this is a kind of complicated diagram here. This is a cross-section through the Pacific. And so here's a little bit of Florida and Mexico, and this is a little bit of South America. And this is just the northeast quadrant of Australia. It's kind of abruptly chopped off. We know that local observations in the 1600s on the coast of South America over here reported that there were occasionally winters where they would get warm water, and they would bring different kinds of fish. And it came often enough at Christmas time that they started referring to it as the El Nino, meaning the Christ child, because this was a blessing. On the other side of the Pacific, there was a series of monsoon failures, including a really bad one in 1866 that was noted by the British who were there at the time. It took them quite a while to gather observations of the pressures. But they started doing statistics and started realizing that if they looked at the pressure in the atmosphere up here over sort of northern Australia and India and South America, that they could predict when these monsoons were going to fail and when they were going to strengthen. And it wasn't until the 1960s when Berknes, again, he keeps coming back, the students were doing a lot of the work, put together the fact that these ocean temperatures interacted with the atmospheric temperatures. And so when we had an El Nino form and when these warm waters came up on the coast of South America, there was actually a pool of warm water moving eastward along the equator towards South America. And it would change the way the rains happened because it was shifting where the low and high pressure systems were. And so while it brought rains to some places, it would bring drought to others. When we started putting the ocean and the atmosphere together, we started coupling what we would call the El Nino in the water and the southern oscillation in the atmosphere. And so the oscillation part refers to this high and low pressure. And early on, we've been able to map where the pressure systems are globally, and we can kind of predict where they are seasonally. But we're starting to see that very small, subtle changes in them can interact and cause this drought or flood, depending on where we are. And so in the 1960s, we're starting to put those together. We had a tremendously bad El Nino in the early 80s that really got a lot of press and a lot of people thinking about just how interconnected things were. And a lot of NASA people were involved with that. The El Nino happens on a 4 to 7 year cycle, and there are shockingly large numbers of things that are related to 4 to 7 year cycles in the Pacific. My favorite is that there is a paper about the reproductive success of foxes on small islands in the Aleutians that happen to have a 4 to 7 year cycle. As does the dentine growth in dolphins. And all these other things. There was just this plethora. And about 10 years later, we started identifying these other oscillations. And in some cases, we had sort of known that they were there, but we hadn't maybe noticed them enough to put them together. And this is just a selection. I could have added another 10 of these oscillations that we now know. So here's sort of the El Nino. We normally know that is being defined off the coast of South America and also off the north coast of Australia. And those pressure systems oscillate back and forth. But we also have the Arctic oscillation, which was first defined in 1997. We have a similar comparable Antarctic oscillation. We've got the North Atlantic oscillation over here. We've got the Pacific Decadal oscillation. We've got the Madden-Julian oscillation. We've got the quasi-biennial oscillation, and there's a whole lot more. And what's fun is they all have different periods over which they work. So the INSO, or the El Nino Southern Oscillation, if you say it really fast, has a 4 to 7 year cycle. The quasi-biennial has about a biennial one, but it's really unreliable. The Madden-Julian can oscillate over 30 days. The Pacific Decadal oscillation tends to majorly change over 20 to 40 year periods. And so all of a sudden, we have these complex shifts in the atmosphere, in that upper part of the atmosphere, that clearly couple with what's going on at the surface. And we're trying to figure out how they work together. And we're still trying to figure this out. If you're interested in whether we're going to have drought in Montana, you can start looking at the combined effects of the Pacific Decadal Oscillation and the Atlantic Meridional Oscillation. And notice, depending on what part of the state of Montana you look at, but if we're over here in Missoula, if we have one of them in a positive phase, and that just refers to which one's the high and which one's the low pressure, we may have kind of an even chance of drought. But if we get them both in a positive phase, we've just upped our chance of a drought to 45%. So these aren't small cases. It's just that they're not super predictable. So there's always the odd chance that it doesn't really happen, because these are multi-year oscillations in some cases, and we know that on a daily basis that jet stream is moving around. And so there's all these interactions that we're trying to sort out now, just to figure out really how the system is working. One of the other things that's really fun, just in the last, say, 10 years that we found, is that when that jet gets really active, we call it an atmospheric river. And these rivers transport amazing amounts of water in them. And they are right along the jet stream. If you've heard of a Pineapple Express bringing a nice warm snowfall from Hawaii, that's one. We now know that they transport an amazing amount of water. This is an example from England, and so they put it in the number of times the flow of the River Thames was coming over, and it was this one event was about 4,500 times that. Here in the U.S., we typically are going to compare them to the flow at the mouth of the Mississippi, and some of ours are 7 to 15 times the daily amount of water coming out of the Mississippi. You could also compare it to the Amazon. In some cases, we're getting about 5 times the flow of the Amazon River in one event. This is an animation showing one event that was hitting California back in 2015. And in the western U.S., about 30 to 50% of our moisture is coming in the form of these really large events. So we're starting to see that, oh, these oscillations and these individual events can really cause pretty dramatic changes to our weather and to our climate as well. I haven't mentioned very much about the chemical composition of the atmosphere, because I don't do very much atmospheric chemistry. But NOAA and NASA were really involved in the discovery and documentation of the ozone hole. In the 70s, Molina and Rowland published the idea that some of the chemicals we were releasing into the atmosphere, if they went high enough up and got into the really cold part of the stratosphere, would have different chemical reactions because it's so cold up there, and because of some of the energy that's being that's present at that altitude. And in 1985, they would be awarded the Nobel for that. But our observations, these were observations that the British were taking over Antarctica using flasks, or the red ones. They discovered in 1978 that the observations were going down very hard, very quickly. And within 2 years, the international community organized and passed an international treaty to limit the release of ozone-depleting substances. And in 2018, NASA had a new satellite that documented the first clear, direct proof that the ozone hole is actually recovering. And so NASA was very involved in documenting that. I also always try to mention this just because if we are talking about big international pollution problems, this is a success story. The U.S. still hasn't ratified the latest iteration of the Montreal Protocol, but what we've done so far is starting to work. If we could do that on some other problems, it would be good. What is NASA doing today? They're still working on aeronautics, and they're still working on the Earth. Dr. Running will talk to you a whole lot more about that next week, what they're doing with satellite record. But in terms of space flight, or flight in general, they are working on making it safer. They are working on making it quieter. And they are making it better in general. They're working on how to develop those unmanned systems that are going to be flying us all around. And a lot of what they do is also related to pollution in other places, like urban areas, for instance, where we're still seeing that kind of, those kinds of pollution problems and trying to address them. And they said that I was supposed to tell you about why I was talking to you about this. And so my research takes place in Alaska, primarily, in the Arctic. And I measure permafrost, which is the part of the ground that freezes and thaws every year. Or pardon me, the part of the ground that stays frozen all year round. The upper part freezes and thaws, but underneath it, it stays solid for at least 2 years. Much of what is currently frozen has been frozen for about 10,000 or more years. But basically, I measure things. I happen to measure permafrost most of the time, but I measure the climate above the permafrost as well. And a lot of our data comes from either satellites that NASA runs or observations on the ground that other colleagues on other research projects are funded under NASA to gather to validate those. And so really what I do is measure things. And so typically I'll install climate instrumentation and also things in the ground to measure the temperatures. And we analyze and look at what kind of changes those are making. And then we can predict how deep the thaw will be if we put in an urban area, for instance. Or if we just stay hands-off and track it over 20 or 30 years. I was not there at the start of this project, but we now have a 21-year record. And we can see that the vegetation is changing in the Arctic and that the permafrost is responding to those changes. My students like the fact that where I work was season 3 on Ice Road Truckers. We do have some research, and it took me a while before I realized that actually I am involved in some NASA research directly funded through NASA, and that's through our students. This is one of my students' senior thesis project this summer. He was out, and this is Jen Fowler and Deb over with the Autonomous Aerial Systems Office, the AASO, here on campus, which you might hear kind of referred to as the drone office. These are the people that are doing unmanned systems for us. And typically they're balloons. In some cases we are using UAVs to put the instrumentation up. They do just like a radio sonde, but they only go up a certain height and then we bring them back down. But we can have them go up and down repeatedly, which is kind of fun. And Max Inger's senior thesis is funded by NASA. And he went out and was measuring smoke pollution during some of the fire events we had here in the area last summer, and then running some models and seeing how these publicly available models compare to look at some of the effects of pollution. And I should say that Tony Ward was really great and loaned us some instrumentation to measure those. But the space grant program is a big part of, I think, how students see NASA. We have about a dozen students on campus that are funded through our state organization, the Montana Space Grant, which is a NASA program that was started in 1989. Jen Fowler at the AASO just published results from one of her projects where she put some balloons up during an eclipse, and they measured gravity waves at the top of the atmosphere. And students were involved. And so we do see NASA really impacting a lot of the lives of our students. And I'm supposed to wrap it up, and I was just going to tell you what I think the next thing is that we're going to learn. And I wasn't going to talk about satellites, but this is a lead-in to next week. You've probably all seen the nightly news. You're looking at the weather satellites. They look something like this. We see part of the western part of the U.S. and the Pacific, part of the eastern and the Atlantic. And, you know, they're nice maps, and we can see a lot. And if there's a hurricane coming, we can see it, and that's really what they've been designed to do. But what comes next? What actually happened a year and a half ago? And that is the launch of GOES 16. Well, before it launched, it was called GOES-R. And GOES-R is the name of the new series of satellites. This is the first new weather satellites for NOAA that were launched in 20 years. And they were designed by this collaboration between NASA and NOAA, NASA putting up research satellites to figure out what works, NOAA figuring out how can we make it reliable. And so GOES-R is going to be the next series of satellites. It's got a lot of sensors on it. First one went up in December 2016. The last one, or the next one, went up in March of 2018. These are going to be our satellites, we think, through 2036. And they are so fun. We like to say that they are 4 times the spatial resolution. We went from a 4-kilometer picture to a 2-kilometer pixel. We went from 5 spectral channels to 16. And so these are the different slices of the electromagnetic spectrum that we're looking at. So there's red, green. We didn't used to have red, green, blue. We just had one visible wavelength. Now we've got red, green, blue. We've got near infrared. We've got thermal. We've got a whole lot more. Back at the very beginning of the presentation, I talked about Espy, who was one of the ones that made those first maps, having people telegraph in information. He had a theory about convection and how that lifted clouds. In the last few years, we have started seeing big, enormous fires. And these big, huge fires actually are starting to cause their own weather, we think. In 1841, Espy, in his book, Philosophy of Storms, they called him the Storm King, hypothesized that if you had a big enough fire, you could cause a storm that could bring rain. He wanted to try it out. People did not encourage him. We are starting to see it. We are starting to see enormous fires that actually put pollution up into the stratosphere, that cause storms so big that they're causing their own lightning ahead of them and causing more fires. We also think they're getting bigger and more frequent, because we've only observed them in the last 15 to 20 years. And this is what GOES-R does. It just lets us watch them. And so if we want to measure them or take data from them, we can do it in 16 channels at a refresh time of about every 5 minutes. So that's where I think we're going to learn our next big things. Thank you. And I'm just going to play it again because it's fun.
Do you know where that is?
This is in West Texas. It was the Mallard Fire last May. It produced a 1-inch hail. So you don't think about a fire as causing a hailstorm.
Okay, if you have a question, if you'll raise your hand, Angela or I will bring you a microphone and we'll get your question recorded on our MCAT program. Here's one right here.
Lately there's been stories about the planet flipping its polarities. In fact, the North Pole is wandering around there right now, and they can't get a good fix on it because it's moving. Now, if it does flip, how is this going to affect the polar jet streams? Or will it?
Well, we haven't observed it do this yet. So we're all going on theory because the poles flip every couple 100,000 years. So we haven't seen it happen. When we look at the geologic record, we can see them happen, and we are trying to figure out how quickly it could occur, because it will probably affect things, but not necessarily where the jet stream is. We don't see that much interference between the magnetic field and the weather systems as far as we know, but once again, we haven't seen it happen, so it could. We think it might take up to 1,000 years, but it might happen more quickly. We also think that it might go into a period where it flips back and forth for a little bit. But what things do rely on magnetic fields? The satellites that we rely on, all of those nice satellites that we just got up, they may have a really hard time responding. All of our computers, we also don't know, there's some, the catastrophic theory is that there will be some sort of a radio pulse, like a magnetic pulse, electromagnetic pulse when this happens, that could just fry our computers. I'm hoping it just doesn't happen for a while.
Any other questions? Oh.
Hi, Anna. Great talk. Thanks very much.
There's no test.
I have two questions about the jet stream. Is the jet stream that we hear about on the nightly news, the northern one, I presume, and is it effectively just a barrier between cold air and warm air?
It really is. But as you saw in the animation, it's so dynamic. And so what we do is we really just connect the dots of where that boundary is. The other thing that is a little bit more complicated is there is a displacement between the upper atmosphere and the lower. And so if we just draw a line around the air mass on the ground, it doesn't quite line up all the time with where, if you think of it as a blob, how squished or pointy that blob is. And so where it is above varies. And we actually get a phasing where the jet will be above the front on the ground, and it will actually help steer where it goes. It's really important with hurricane steering. When that coupling is right, that jet will just tell that front where to go on the ground, and there will be this great coupling between the upper and the lower atmosphere. And then it'll last for 3 to 5 days, and then it can get out again, and then and that's when that jet weakens, and then forms again.
And then what about the southern jet stream? I don't know that we ever hear about that on the news, do we? And what would its effect be?
If you watch Australian weather. But otherwise, we just don't talk about it. It's hard even to find a diagram that has the 4 jets on it because we're so centric to the U.S. The Antarctic jet is just really pretty well behaved and confined, but the subtropical one brings weather to the Amazon and those kinds of things. And there are some really nice weather sites now where you can go and you can just see the whole globe, and then you can see all 4 jets, and they move around and strengthen and weaken.
Well, I was amazed to see your picture of the Japanese bomb, because one actually did land outside of Butte, and my father worked for the highway department.
Oh, wow.
And they called up, and it had exploded, and so it was in pieces kind of in the woods. And then they were told that you couldn't tell anyone. There was an absolute silence, and of course, I was a baby then, but when we grew up, we had a big piece of it that was all folded up in a box, and it was this sort of leathery, creamy material with Japanese writing on it.
Oh my God.
And he actually told us, he said, we found it, we knew it was a bomb, we told the police, and then we were absolutely silenced and could pick up the pieces, and some of us brought a few home, and then they took the rest. So it was a true story.
That's amazing. Wow. They found one in Canada in 2014 and sent in a bomb squad to deactivate it. It hadn't exploded. And so if you do see what you think is part of one, don't go up to it unless it's really exploded and you can tell that it's like little bits. But yeah, and it's interesting because we have reports of 300, but they think 900 made it, so there should be more out there. Wow.
Thank you. Is the jet stream predictable so that we know, when airplanes fly, that would be my main understanding of it, are airplanes able to Well, is it predictable for them? And my other question is how do you expect global warming affects the jet stream?
We can predict the jet pretty well up to a couple days ahead. And they'll even show that on the nightly news sometimes. This is the 3-day, kind of, or the 5-day. And so with airplane travel, we will divert. Actually, if you're heading east, we'll divert you into the jet. I think. Is that the right way? It is harder standing up here. And so they'll take advantage of that. And they actually count on it to make their time quite often. Those schedules are pretty quick. But if they know the plane is going to be an hour and a half late and hasn't taken off yet, probably is, or could very well be because they know that the jet will be, if you're flying west, you're flying into the jet. If they can't deviate around it, they'll get hit by it. Yeah. We fly on lines of pressure, so we are very careful to know where that jet is because it's also on the pressure. And with climate change, we do think that it seems as though, and it might be because of a difference in the temperatures between the Arctic and the tropics, changing that ratio, that the waves are getting deeper and more frequent. And especially it seems like it's happening during the winter. And so those cold outbreaks, I believe Ohio had temperatures close to 0, and then 5 days later, 60 degrees last week. Those seem to be getting more common because the jet is allowing those air masses to go deeper and then further north. Alaska is getting a lot warmer spells, too. And Canada is as well, not as much as Alaska. And Europe is getting the same thing. So there's a lot of work being done right now to try to figure out why the atmosphere would do that, but it seems there's definitely quite a few people that are starting to think that this is something that will happen, and it's because of that change in basically how warm the Arctic is. They actually call it a warm Arctic phase now. It makes the meanders in those jets bigger.
So with, like, when you're talking about climate change, does that change not only the warmth but the cold of the atmospheres? Does that make sense?
We still get the cold air masses forming over central Canada.
Mm-hmm.
But it's possible that they won't be as cold in the future, or that they won't be, that the ones that were the coldest will be much rarer, and the ones that were almost as cold will be the ones that we see more typically. So we're shifting, so all of them, we're shifting so that generally warmer is happening. Mm-hmm. But we also think that the extremes might be happening more. And so what was typical is just not going to be happening as often. So we might be getting more extremes of the hot and the cold, but overall also generally warmer, which is a complicated answer. Sorry. But so the cold will not be as often, but the hots will be hots that we haven't seen before, even in the winter.
Thank you, Anna, for this very informative talk. I'm curious about your own research. You spoke a little bit about measuring the permafrost and changes and how the vegetation has changed in response. Mm-hmm. Can you elaborate on that a little bit?
So what we are seeing Arctic-wide is that in areas that don't have trees because there's frozen ground underneath them, so there's not the roots to support that, that tree line is going further towards the poles, and that shrubs are going further towards the poles, and that they're getting taller as they go. In most parts of the world where there is permafrost, the active layer is getting much thicker, except in our study area. And we realized that it probably would be, except that where we do our measurements, we coordinate a network, so we coordinate the other people's network, the other people's measurements into the big database. And most places are seeing this thickening of the part that freezes and thaws every year. In Norway, we can't measure it anymore. It's dropped several meters. We can't reach it anymore by standard methods. Even the boreholes, they're 50 meters deep, are starting to lose it in Scandinavia. In northern Alaska, we're doing pretty well, except that we realize we're freezing and thawing about that much, maybe 2 or 3 feet each year, where we have all of our oil and gas infrastructure. But we realize that the whole surface is sinking. So as we're thawing, we're actually thawing the upper part of the permafrost and just sinking the land, which is a little bit of a challenge for engineering. And we're trying to figure out how widespread that is. And it's not that much. We've only seen about 10 centimeters over a decade, but that's still a pretty substantial amount. And when we talk about the oscillations, the Arctic Oscillation changed phase in 1977, and if we look at really old data records, the permafrost and the active layer dynamics were different in the 60s than they are today. And we have measurements from World War II through the 60s, and then there was a break, and then we had them again starting in the 80s. And we think there was some resetting of the permafrost levels. And so coupling and decoupling what's affecting what is pretty complicated. And unfortunately, permafrost, it responds to the ground below it, to the vegetation on the top of it, to the snow you put on it. And so if you have a shrub over here and a shrub not there, you get a different response, and your permafrost surface can actually go up and down quite a bit. It's really frustrating. We spend a lot of time describing how much variability there is in this.
Any other questions?
Hi. I just have a quick question about the jet streams again. When you showed the first slide that showed 4 and sometimes 5 jet streams, there was that 5th one that I may have misunderstood, but it sounds like it came and went during the year.
It's usually in the summer.
And I was wondering why it does that, and if there's anything about that that hints that could you, with a change in climate, have one of the other 2 major jet streams in the north or the south also perhaps disappear eventually?
So the one, the equatorial jet, it tends to form near the Himalayas, and so you get a sort of air masses on either side of the Himalayas because of their tremendous height. And so it forms periodically, but pretty reliably in the summer for a couple of months. But it's unpredictable in that it sometimes starts and stops. Sometimes it just starts and lasts for the season. And I know there has been some work tying it to the monsoon, how long it lasts versus how the monsoon responds. But I just don't know that much about it. I feel like as long as there are differences in the air masses, that these jets will form. It's just they may not be very strong. And so one of the things we had thought we might see was that we thought the jets might slow, like just all of them might slow, if there isn't as much difference in temperature between the tropics and the poles. But no, what we've been seeing in the last few winters is that the meanders are getting bigger, and so the jet's actually being faster, which isn't what we thought, but,
Do you know if anybody has done any research to manipulate the atmosphere to change the weather?
Oh, yeah. Yes, Espy was proposing it back in the 1800s, and we actually do this. It's a couple of winters ago, Nevada was worried that they weren't going to get enough snow or rainfall, and so they paid some companies to do some cloud seeding. And it works for a while. It's just that you have a certain amount of cloud cover coming in, and if you cloud seed, then that rain will rain out. But you have to be predicting really well where those clouds are going to go and how much of this compound that you need to put into the clouds. And so sometimes it works really well, and sometimes it doesn't work at all. When Nevada tried to do it, there was some upset because California got a little annoyed and were being very protective of their snowpack. And then there was some contention that maybe that was taking rain from farmers further east. And once again, the success rate is not so great. So we keep playing with it. And there are multiple companies out there that you can hire to do that. They're pretty expensive. One of the fun ones, Bill Gates put some money into some research to see if we could find a way to put something down on the surface of the ocean to prevent a hurricane from intensifying. And basically we would dump oil, vegetable oil of some kind, in front of the path of the hurricane to prevent the water from evaporating in front of it to fuel the system. They haven't gotten too far with actually trying that out because they think that you might have to put a fair amount of oil down to prevent the wave action from just dissipating it. But that's one that we've really talked about too. Before we thought global warming was a problem, the Russians wanted to distribute ash very widely over Siberia to try to melt the snow off in a big way to make it warmer so that they could grow more crops. So we've come up with some creative ideas. It's just so far they haven't really been too beneficial. But the Soviets also made rivers run backwards, so I mean, some of these things can be done if you try hard enough.
One last question. Is there one last question? Okay, well, there's one.
Oh. Sorry.
Is there any relationship between the rising temperature of the oceans and the behaviors of the jet stream? I mean, I've heard, for example, that the ocean's temperature changes enough, the warm currents that moderate the climates in Europe may get cut off, and the jet stream may bring nothing but cold air to them, and they may experience much colder weather than they're having now.
We definitely are seeing warmer waters in some places, and I think the El Nino is a very good example of the fact that if you shift where that warm water is, climate systems shift. The last, probably from 8 to 3 years ago, but I think it's still sort of there. Off the west coast of the U.S., we had what we called the blob, and it was a blob of warm water that was from Oregon north to Alaska, much warmer than it should be. And we did see it shift where the jet pattern was going, not all the time, but the frequency of where it was shifted. The fish were different. They think that might be tied to the die-off of the starfish. There's all sorts of things that seem to be related to that. Some of the drought frequency we've had in the West is definitely tied to the fact that there's a high pressure forming, partly because of that blob being there. We don't know where it came from. But yeah, if we start warming the oceans, they will do things. They'll also put more humidity into the atmosphere, and so we may see an intensification of the hydraulic cycle in general. At least we assume we will. Yeah.
Okay, thank you, Anna. And we'll see you back here next week, Tuesday at 7 o'clock.